Today we're going to be continuing to look at limits at infinity. And eventually we do want to take a look at shortcuts that we can use and also shortcuts that we should avoid because there are assumptions that are essentially wrong. This one is a great example to start with. When looking for shortcuts, it is tempting to see that pretending like as x gets really big and we're subtracting x to see what we actually get. Right? So when taking a look at this, it's tempting to see that, well, maybe x squared and x, the degree is lower, so as x gets big, this difference, this will become minuscule. And maybe this will become the square root of x squared, closer to the square root of x squared, which is x minus x. So it's almost the same. It seems like it's tempting to say infinity minus infinity is 0. Right? So this would be almost like x minus x as x gets really big. This is actually a wrong assumption. And if the answer happens to be 0, it would be by accident. Infinity is not a number, it's an idea. So if you can't really see the limit of an infinity minus an infinity. So how do we solve this? What do we like? What can we assume? Whoops. So one of the theorems that we did learn was that the limit as x approaches infinity of 1 over x approaches 0, right? Now, if you write something like 1 over infinity is 0, this is actually a strange statement. You can't divide by infinity. There is no statement as this. I understand the idea, but infinity is not a number that you can plug in. But this right here is a theorem. And the same goes for pretty much if there's any constant up here, compared to when x gets closer and closer to infinity, any constant will be almost insignificant. And of course, x to any power will get this closer and closer to, well, when n is greater than 0, right? This will get closer and closer to 0 even faster, the fraction, right? So like, for example, 1 over x to the 4th. This denominator will get bigger faster, dropping it down to 0 faster. So now this is a theorem that we are allowed to use. The fact that 1 over x to some power, or a constant over x to some power, is equal to 0. And we like this form. Now in this case, we're going to try to use this theorem in order to figure out what the limit is here in our example. Now, again, for all of these, we like fractions. We like some sort of rational fraction. And in this case, because there's only a 1 on the bottom, I'm going to try to manipulate this to move some of the x's to the bottom. So I'm going to multiply by its conjugate. Plus x, right? All over the square root of x squared plus x. Right? Let's see what we get. We get, obviously, a squared minus b squared. So a squared gets rid of the square root minus b squared, which is x squared, all over this denominator, the square root of x squared plus x plus x. Now in this case, my x squared minus x squared equals 0. I'm left with the limit as x approaches infinity. It looks like I have an x on top. Then I'm going to try to cancel with one of these x's. Well, I can't just cancel this x and this x because this x is embedded in the sum. So I'm going to leave that x on top. I'm going to factor out, I'm going to try to pull out an x from this square root. So the only way I can pull it out is by finding the square root of an x squared. So I'm going to, out of these two terms, I'm going to factor out an x squared, and I'm going to be left with 1 plus 1 over x, and then I'm going to have this x left over here. If you take a look, I'm going to distribute it back in order to see, double check whether I did that right. So x squared times 1 is x squared times 1 over x is x. Now if you take a look, it looks like, I'm going to show all my work. X is still on top. Square root of x squared is just x. I'm left with the square root of 1 plus 1 over x plus the extra x out there. And in this case, what I'm going to get, this x, I'm going to factor out the x from out here, left with square root of 1 plus 1 over x plus 1. And now these two will divide to 1. And I'm going to be left with something that looks like this. And now if you take a look, now we know, let's see if we can, right? Now we know in this larger fraction, in the denominator, I have all my x's. And in this case, as x gets really, really big, this will approach 0. So what is the limit of this initial function as x approaches infinity? It's 1 over the square root of 1, this is 0, plus 1. It's actually equal to 1/2. Now this is not something that you could have used a shortcut for. This is not something that you could have assumed from the very beginning, because it's too tempting to assume that it's equal to 0, like an infinity minus an infinity, right? So let's take a look at some shortcuts that we are allowed to use. In this case, we have 3 examples, and I'm going to note the difference between these 3 right now. In the first rational function, we have the numerator with an x squared on top, a denominator with x cubed on top. So the numerator's degree is lower than the denominator's highest degree. In the second one, the numerator's degree is higher than the denominator's degree. So this is a degree of 1 here. In this case, it looks like I have the square root of x to the 6th, which is x cubed. That's the highest degree in the numerator. And on the bottom, it's the same x cubed. Okay, so this one, the degree on top and bottom, are actually the same. We're going to take a look at the difference between these. So when I solve something like this, I'm going to multiply both sides, top and bottom, by 1 over x cubed, the highest degree in the denominator. Distribute in, I get 1 over x cubed minus 1 over x, all over 1 minus 1 over x squared plus 1 over x cubed, right? Now this will approach 0, this will approach 0, this will definitely approach 0, definitely approach 0. I get 0 over 1, which is 0. The limit of this function is 0. The next one I'm going to do is this one, where the numerator is higher than the denominator. Now in this case, it's tempting to multiply both top and bottom by 1 over x squared, the highest degree in the entire fraction. However, if you do that, the highest degree in the entire fraction will make the other side equal to 0. So if you divide top and bottom by x squared, this is going to become 3 over x squared minus 1 over x. So this will become 0. The denominator, if it becomes 0, it does not exist. So if from here you did that and you get does not exist, it's correct. It's not wrong. Because technically, if it goes to infinity or negative infinity, it does not exist. However, to get more specific, to see what kind of a vertical asymptote we might have, we can instead divide top and bottom by the highest degree of the denominator. So 1 over x. So I'm actually going to multiply top and bottom by 1 over x. Now let's take a look at what happens. I get x plus 1 on top over 3 over x minus 1 on bottom. Right? So in this case, I'll get, this will approach 0, and it looks like I'm going to get something that looks the same as this. Now this is a lot more telling than does not exist, right? Because it tells me more specifically what this limit will approach, which direction it will go. Because as x gets really, 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 really big here, I still have to divide by a -1. So this limit will actually approach negative infinity. Again, same thing as does not exist technically, but a little more telling on what the graph is. So we're going to set that equal to negative infinity. And this is what I'll be expecting on the homework and on the tests. Okay. So now the last one. This one, it looks like the highest degree in the denominator is x cubed. In case you need a refresher on how to do this, the denominator is easy. X cubed divided by x cubed is 1. 1 divided by x cubed is 1 over x cubed. On the top, however, this is inside a square root, so I need to put this in a square root. But I can't just square root it and change it. I got to square root and square it. That's a times 2 there. Right? That way it's essentially the same thing as x cubed. So then on top, I'm going to get the square root of 9. Sorry, I'm going to do the whole thing. Square root of 9, and then it's x to the 6th over x to the 6th. So it's just 1. Minus x over x to the 6th. So 1 over x to the 5th. Right? So in this case, what happens as x approaches infinity? This term will approach 0. This term will approach 0. I get the square root of 9 over 1, which is just 3. Okay? So that's showing all the work. You have to know how to show all the work in order to be able to use shortcuts. So let's take a look at why we chose these 3. Okay? Now these I'm going to move aside or delete. Alright, so let's take a look at the top 3 functions that I chose. Okay? In this case, when the numerator's degree is lower than the denominator's degree, basically this denominator will increase significantly faster, a lot faster, where the limit will become 0. Okay? In this case, when the numerator's degree is smaller than the denominator's degree, this will become 0. Because really, if you take a look, if I divide this by x cubed, x cubed, x cubed, x cubed, x cubed, this is always the highest degree will still become 0, as well as everything before that. Right? So now in this case, if the numerator's degree is higher than the denominator's degree, so this is a degree of 2 and this is a degree of 1, then this numerator will become larger a lot faster than this denominator, making it a plus or minus infinity. You just have to think about whether it's going to be positive or negative. So this is always going to be positive, and then this is always going to be negative, because beyond the number 3, as x gets infinitely big, 3 minus a really, really, really big number will be negative. So this will be negative infinity. And you can do that without doing all of this work. Okay? In this case, as long as you can see that this is the square root of x to the 6th power is the degree. So this degree, the highest degree in the numerator, is actually 3, not 6. It's 3. The degree in the bottom is also 3. If that's the case, the coefficients is what's going to matter. So there's a 1 here, right? So this will be the square root of 9 over 1. So this will become 3. Right? So here are the shortcuts. You are allowed to use these shortcuts, remember, only for rational functions. So a polynomial on top of a polynomial, right, as a fraction. But if I go backwards to an equation like the first one that we've done, something like this, you are not actually allowed to assume any kind of infinity minus infinity. So be careful when you use the shortcuts. And that's it.